Hope everything is going well and you're being safe and everything else. Today, we are going to work on chapters 2B and chapters 3, so 3A and 3B together. Out of everything we're reviewing, this is probably the one concept that you forgot. Like inverse derivatives here, this is the one that everyone, as I do it, is always like, oh yeah, I don't remember doing that. And it's been a while. I'll get it figured out for you here, but just work through it. Again, I know that you're got a lot of other things on your mind and things like that, but we're just trying to review the process. The good news is we are to review, so that's all we're working on. I'm not going to be a huge stickler for due dates. I want you to stay up on it, but try to get stuff done. You got 3 weeks off here at least. We're trying to learn some calculus. I know everything else is crazy. This is the one thing that's giving me focus and making sure I'm doing my job because that's what I do well at. So ask me questions, live sessions, come and see me. Let's talk about stuff. Keep us entertained. Here we go. All right, so fancy derivatives was the name we gave chapter 2B, mostly because it was just derivatives, but the weird ones that you don't interact with every day. First thing we got up here is implicit differentiation. Remember, that's like when you take the derivative of xy. So if I took the derivative of xy, you would need to use product rule, but basically you just take your derivative like you normally would, and then you get to multiply by dy over dx. And that's going to apply a lot of times, not just when it's y, but if it were taking the derivative of h or anything like that, if you're not taking it with respect to h, then you got to include that aspect to it. So dy over dx is the key to implicit differentiation. We'll look at that here in a minute. Remember what derivative e? Derivative of e is what you see times the derivative of the exponent. So let's do this a little bit different. E u times u prime. That's going to be our derivative right there. A reminder of the silly version one. If I said what's the derivative of 4u, it would be times that times, what's the derivative of 4x? That would be 4x times the natural log of 4. That's something we didn't go over a bunch. Don't really care too much. The derivative of e is what you see times the derivative of the exponent. What's the derivative of natural log? It is 1 over the baby. So let's call it u. So 1 over u times the derivative of the baby. And then we got chain rule. Something like f of x or f of g of x. So if we were taking the derivative of f of g of x, you take the derivative of the mama, you rewrite the baby, and then you multiply by the derivative of that baby, so g prime x. Boom, there's my setup there. Chain rule. Inverse functions. Remember how inverse functions work, okay? A reminder, and again, I know you have forgotten this, but remember what an inverse function is. This function right here and this function right here are inverses of each other. If I took this point right here, this is the ordered pair 2, 1, that would match up on the other graph at the ordered pair 1, so that would be 1, 2. And this slope right here would be the opposite slope or the reciprocal slope of that one right there. They're the same, but they're different. Okay, so if you flipped the x and the y, the slope of this point at 2 is going to be the same as the reciprocal of the slope at 1. It's a little bit much. If you want to go back, look at some videos there, inverse functions, you can see what that looks like. All right, so look here, if they gave you the 0.37, that's the original function. We are trying to find the derivative of the inverse at 7. So the inverse at 7, if this is 3, 7, that's 7, 3. F prime of 3 is 4, so the reciprocal is 1/4. We will do one of those again, but that's out of anything that we've done, this is always true every single year. This is the one where students are like, I don't remember how to do derivatives of inverses. Don't let it be weird. And then inverse trig. Remember, inverse sine is 1 over the square root of 1 minus the baby squared times the derivative of the baby. Inverse tangent is 1 over 1 plus the baby squared times the derivative of the baby. Remember the difference, square root, and then plus or minuses. Related rates, that's in this chapter as well. We'll get to that here in a second. If you're taking the derivative of that, h prime at 0, this is h, I don't know where letters go. If that's h, finding h prime at 0, well then you got to take that derivative. First I would say rewrite that as f of x to the 1/2 power multiplied by the exponent. rewrite the baby, subtract 1 from my exponent, times the derivative of the baby, f prime of x. Then you just got to go back and plug in 0, and then work from there. But that would be the derivative. Set it up from there. Same thing on number 2. You're going to need chain rule. That's the baby. Multiply by the derivative of the baby, things like that. You can check your notes. I'd like you to rather try those on your own than me doing them. This one right here, this is going to be an implicit problem. Okay, so remember what this looks like. When I take the derivative of the xy, that is, I'm going to have to do product rule. So first times the derivative of the second, the derivative of y is going to be dy over dx, plus second times the derivative of the first, that would be 1, minus 2y, well the derivative of 2y is 2 dy over dx, and that's going to be all equal to 0 there. Don't forget to put the 0 in there when we multiply. Or when we take the derivative of 1. All right, cool. We got it. Now you're plugging in 3 and 1, so just plug them in. 3 times dy over dx plus plug in 1, so 1 minus 2 dy over dx is equal to 0. Combine like terms. So 3 dy dx minus 2 dy dx is just going to be dy dx. And then I'm going to move that 1 to the other side, so it's going to be all equal to negative 1. Boom, done. Ooh, we look at this one. We see inverse. So as soon as we see inverse, we're thinking about the original and the inverse. In the end, since I'm trying, remember we're setting up ordered pairs. In the end, since I'm trying to find g prime at 2, that is the ultimate goal. What is g prime at 2 going to be? So that means this is 2. That makes this g. That makes the other one f. If this is 2 comma something, this is something comma 2. I need to know this number right here because my ultimate goal is going to be find f prime at that number, which is going to be the same as that number. And then whatever I get right here is what's going to go right there. I'm going to do the reciprocal. I'm sorry. Let me try that again. Whatever goes right here, the reciprocal is going to go right there. All right, so we got to find that x value. So what we're doing here, f is this, and this is the y value. So we're going to come over here and say x cubed plus x is going to be equal to 2, because we want to figure out what x value is going to get me to. And so we could do some solving. I'm going to use my brain here and know that if I plug in 1 cubed plus 1, oh yeah, that would get me 2. So my x value is 1. That means I want to find the derivative at 1. So that means I need to find f prime of x. Well, there's that. Take the derivative of it. Plug in 1. And then I plug in 1. 3 times 1 is 3 plus 1. That's 4. Lovely. I'm doing the reciprocal of that. So it'd be 1/4. If you need more practice with that, jump on Khan Academy. Obviously, Schwann Academy has links to that as well, but that would definitely be something I look at because it's going to be 1 question on your AP exam. It's not going to be 50, so you don't have to be great at it. But at the same time, if you are good at it, it's really, really easy. And so that's why I like jumping over it because I think for the most part, it's pretty straightforward. Let's do one more here. The radius of the base of a cylinder is decreasing at this equation, or at this rate. So that's the radius is decreasing. The height is fixed, so it is not changing. At a certain instance, when the radius is 40 kilometers, what is the rate of change of the volume of a cylinder? All right, so the key to this is to know the volume of a cylinder. The volume of a cylinder is height times the area of the base, so pi r squared. So that's my formula. Let's see what things they told me. Well, they said the radius is decreasing at that right there. Or in other words, the change in radius over time is negative 12 because it's decreasing. The height of the cylinder is fixed at 2.5. So the change in the height over time is 2.5. I'm just playing. Just kidding. The change in the height is 0. Height is 2.5. It's not changing, though. It is a constant. So remember, we're going to plug in constants and do some different work with that, but that's true. At a certain instant when the radius is 40, so when r equals 40, what is the rate of change of the volume? So ultimately our goal is to find dv over dt. So we've got all our things labeled. We've got our equation. Now, if we want to talk about rate of change, we are going to take the derivative. Remember, before we take the derivative, we can plug in anything that's going to be constant, because if it's constant, it's not going to change, so it doesn't have a derivative. So, for example, here, we've got this h. We can just plug in what h is. It's 2.5. So this is 2.5 times pi times my radius. I'm not going to plug in radius because it's changing. That's my formula. Now that I've got my formula with constants plugged in, I'm going to take the derivative of this guy. So v is dv over dt, 2.5 times pi times 2r, and then times dr dt, because it's the change in radius over time. So my answer here is going to be dv dt equals 2.5 times pi times 2 times 40 times dr dt. And we could plug that all in and get an answer there, but that's going to be good enough for me. Hope that makes sense to you. Again, we could do a lot of simplifying with that. I was looking at my answer key and checking to make sure I did it good. I did. But you could do things like, 2.5 times 2. Yeah, that's going to be 5, and make it simpler that way. And do a lot of more simplifying. I'm just going to leave it. That's my answer. That is what's going on there. So remember, we identified our equation, identified what things were changing and labeled stuff, plugged in constants first, and then took the derivative and plugged stuff in. That's rates of change. Now we get to this stuff. You guys should probably be pretty good at this. Applications of derivatives, looking at graphs. Again, I hope I don't have to do a ton here, but let's look. You can fill in this chart. You look it up. You got it everywhere. It's on the notes too. I don't think I need to talk through all of that. Probably the one that we forget, inflection points. Then is when f prime changes slope signs. So f prime has relative extrema. So maxes and mins on the inside, not including endpoints. The one thing that we kind of screwed up the last time we did this was points of inflections do not happen on endpoints. Okay, remember that points of inflections do not happen at endpoints. That is a key. I've gotten some answers lately with that being true, so don't let that happen. When trying to find maximums or minimums, what do? Well, we take the derivative. You set it equal to 0 or maybe undefined. If you got a fraction like 3 over x, then you would want to look at 0 as well. We take the derivative, set it equal to 0 or undefined, and then you do a sign chart. Remember what that looked like? You got a little f prime sign chart. Boom, number line. Hey, we had a 0 at 2 and it went negative to positive, so that would be a minimum. If you are trying to find a point of inflection, find the second derivative. Set it equal to 0 or undefined. And then you check your sign chart. This time it doesn't really matter what it does, whether it goes from positive to negative or negative to positive. As long as it changes signs, then you're good. If you're looking for intervals that are increasing or decreasing, guess what? Take the derivative. Set it equal to 0 or undefined, and then sign chart. A lot of different things can be solved by taking the derivative, setting it equal to 0, and solving. Just got to know how to do each one. Again, nothing crazy difficult there. Just make sure you do it. Okay, so for example, if you wanted to find the values where this thing right here has local extreme values and points of inflection, take the derivative, set it equal to 0, sign chart. Take the second derivative, set it equal to 0, sign chart. Work from there. You can look at the answer key, but it would look something like that. I was going to write this out, and then I thought, I got it all written out right here. Okay, and so again, it's more about looking at it. Sorry, it's not letting me zoom like I want to. Take the derivative, set it equal to 0, sign chart, boom. This is a positive because it changes from positive to negative. That's a minimum because it changes from negative to positive, increasing, decreasing intervals. Then we would take the second derivative, set it equal to 0, solve it, put it on a sign chart. since it changed signs, that's a point of inflection. It's concave up when the second derivative is positive and concave down when the second derivative is negative. Okay, nothing groundbreaking there, just what you need to look at. Make sure you can do it. You've got a cool little graph right there. I'm confident in your abilities to go through and look at it. I'm going to go ahead and just do it and justify it, and then I'll turn it back on here in a second. I don't think I need to talk my whole way through each one. All right, pause it if you haven't gotten a chance to do them yet. I want to see if you know what you're doing. We're looking at this graph. Again, the key is justifications. Make sure we do justifications before you do anything else. It is an F prime graph. So if it is an F prime graph, every justification needs to be in terms of F prime. F is decreasing, F prime is negative. Point of inflection, F prime has relative extrema. F is concave up, means F prime is increasing. Local maximum is when F prime changes from positive to negative. Well, F prime never changes from positive to negative. Here it changes from positive to more positive, but there's really no relative maximum here. This would be a maximum and that would be a maximum, but it would not be a local maximum. And so we're not including them there. What is F double prime? Well, we're going to look at slope of F prime. F prime is decreasing, therefore it's negative. And then what is the slope of the tangent line at F of 2? This is a graph of slope because it is F prime, so it would be 0. Hopefully you did well. Again, if not, the first couple days we are doing those live lessons. Come and talk to me. I'm bored. You're bored. Let's get together and be bored together, and we can learn some math along the way. See you guys. Let me know if you have questions. Text me on Remind or whatever else you need, and we'll go from there. Thanks.